YouTube, go to my website, right? Check out at the bottom underneath the calendar, watch classroom videos. It'll take you to a link with a playlist of YouTube videos, all that I've done on the smartboard, except they're not organized as well as I'd like. Some of the ones you want might be in the beginning. Most of them are probably going to be at the end, right? So you probably need to scroll all the way to the end of the video and click on whichever one that is. Now, re-explaining this problem. I have a 9.7 positive nanocoulomb charge, right? And then I have electrical potential lines, if you will, right? Equal electric potential lines, A and B. In other words, at those spots, the voltage is still the same, right? The voltage is the same all the way around those spots. I take a proton, I put it at A, I release, I let it go to B. Series of questions, 1, 2, 3. First one. Find voltage at A and B. Now this one was just plug chug. Okay? This one was just plug chug. V equals K Q over R. Right? I'm trying to figure out the voltage at those points. What's causing the voltage? The 9.7 nanocoulomb guy. Right? Does everyone see that? So this is going to be for the 52 voltage, because voltage at A will equal K, which is 8.99 times 10 to the 9th times Q, 9.7 times 10 to the negative 9. Why negative 9? Nano, good. 9.7, thank you. Okay. Divided by the distance between them, 0.52. Not 0.52 squared here, this isn't R squared, this is just R, 0.52. Right, so give me VA, please. 167? Yes. 167 volts. If I was rounding for sig figs right here, what would it have to be? Yeah, 170. Those would have to become 170, right, for sig figs. Units, volts. Now, VB, you repeat the exact same process, right? VB is going to equal 8.99 10 to the 9th, 9.7, this should have been 7 up here, excuse me, a times 10 to the negative 9th, because nano, all divided by the distance was 79 centimeters, 0.79. So, what is the voltage at B? 110. 110? 109 point what? 110.4. 110. Blah, blah, blah. Right? 110. Okay, there we go. So there's the answers for number 1. Number 2. Number 2 asks, how much kinetic energy does the proton get? Right? So, get myself some room here. Actually, over that way. How much energy does the proton get? Now I'm going to want to use an equation that deals with energy and the little charge, right? That's work equals negative Q delta V, right? Work and energy are the same thing. Work energy theorem. Work and energy are the same thing. So W equals negative, let me get a little bit more in here. W equals negative charge of a proton, which is what? Times 10 to the negative 19 coulombs, good, times the potential difference, right? It's V final, that's 110, minus V initial, 167. Negative and negative, this guy is going to come out to be a negative number, right? A negative up front tells me how much work, how much energy did it gain. Give me the answer for this, please. 9.1 times 10, negative 18. 9.1 times 10 to negative. Is that what everyone's getting approximately?
Yeah.
Unit. Joules. Joules. I plugged in coulombs. I get out joules from this equation. Good. Last but not least, what is the final velocity of this proton, right? So what is this guy's final velocity? Well, work is the same thing as kinetic energy, or change in kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. Yeah? And what's the initial velocity that we can assume? 0. Then the entire thing goes away. That leaves me with 9.1 times 10 to the negative 18 equals 1/2 the mass of proton, 1.6 what? 1.673, 10 to the negative 27, correct? Vs squared, final velocity equals
1.0 times 10 to the fifth.
units. Good, meters per second. Now, last question you have to ask, is it realistic? Yes, yes. Oh, unrealistic answer that you might question yourself, and then you'd question me if I set it up right, would be anything times 10 to the 8th. Speed of light is 3.0 times 10 to the 8th. If you were coming out with something at the speed of light greater than the speed of light, not happening. Okay? Whenever you start approaching the speed of light, you're getting into times 10 to the 8th, so you're getting relativity. We haven't gone over special relativity yet. You don't want to go over special relativity in these problems just yet. Okay? We'll do it at the end of the year. It'll be a lot of fun. Okay? Not just yet, though. Nothing goes faster than the speed of light. This is still slow enough. It works. A proton, when put through a decent-sized voltage, like this, a human-sized voltage, let's say, you know, we're in the hundreds of volts, it's big, it accelerates. Right.
I multiplied instead of dividing on something like that, so like negative 0.7.
Gotcha. Yeah, be careful with your math. Now, I broke this down in 3 parts for you, right? I broke this down to all 3 parts. I might not have broken it down to all 3 parts. I might have just asked at the very beginning, question number 3. What is the final velocity of this proton giving you this setup? Not necessarily having drawn it out, right? I could just type it out in words. There is a 9.7 nanocoulomb charge. A proton is brought near, this knot is brought to within 52 centimeters of the 9.7 nanocoulomb charge. It is then released and allowed to move to the 79 centimeter, or move to 79 centimeters away. What is its final velocity? Okay? All in one fell swoop, right there. Those are the 3 pieces you would have to do to get there. Lots of times, I like, if it's all 3 pieces together, I like to combine piece 2 and 3 into this guy. Work equals negative Q delta V, that's change in kinetic energy, equals negative Q delta V, that's my 1/2 mv final squared, 1/2 mv initial squared equals negative Q delta V, and the initial goes away, and it's those 2 pieces all day together. Okay, that's the way I like to solve it. Let's work another problem. Based off of the exact same thing. What if I didn't stop? What if I didn't stop it at B? What if I didn't stop this proton at B? I let it keep on going. I just let it keep on going, right? Where would the proton technically stop? Never. Never. At infinite distance away. I'm going to let this proton go all the way out to infinity. Infinite distance away. If I'm not going to stop it, it's just going to keep on flying, right? Object in motion wants to stay in motion unless acted upon by an outside force. I'm going to let it move all the way to infinity. Okay? I'm going to let it move all the way to infinity. So down here, I'm going off the exact same thing. This is another question. I'm letting the proton go from, that was a 52 centimeter mark for A, is that correct? From 52 centimeters to infinity, all the way out. all the way up, possible. And this is a lot easier than you think. You already solved for the voltage at the 52 centimeter mark, but we had VA, right? What is VA? 167. Now, what is the voltage at infinity? Good. Zero. Zero. Here's why. V equals KQ divided by R. Plug in infinity in for R, right? You got to do it conceptually, right? See what, those of you who are starting to calculate stuff, limits, right? You're seeing what is flow sheet, right? The idea is plug in some number for R, let's say 1, right? And plug in some number for Q, just to make things easy, right? We're talking the entire numerator, let's say, is 1. And then I'm going to plug in a number for R, 1. 1 divided by 1 is 1, right? And now I'm going to get that R closer and closer to infinity to see what happens. So now I'm going to do 1 divided by 10. 0.1. It's getting smaller. 1 divided by 100. 0.01. Right? And I keep going and going and going, and the closer and closer I get to infinity, the closer and closer I get to 0. So an assumption that we make with math is that the voltage at infinite distance away, whatever infinity is in the first place, must be 0. Okay, so this idea right here, something you just have, right? You don't have to go back and calculate that. Voltage infinite distance away is 0. So if I'm asked, the proton goes from 52 centimeters to infinity, what is the final velocity of this proton? If I just let it keep on going, what would be its final velocity all the way out there? That's just this. Work equals negative Q delta V. Work equals negative Q delta V. That's change in kinetic energy equals negative Q delta V. 1/2 mv final squared minus 1/2 mv initial squared equals negative Q delta V. Once again, we can assume the initials are, the initial is 0, the velocity, right? That leaves me 1/2 m velocity final squared equals negative Q, change in voltage. Now let's plug in numbers here. Okay. So that's 1/2 mass proton, which is 1.673, 10 to the negative 27. Vf squared equals negative 1.6 times 10 to the negative 19th. Is that correct there? Or did I botch something? Good. Okay. What's the final voltage?
0.
0. And the initial voltage, where it starts out at, is 167. 167. And now let's calculate the Vf, exactly where you already actually did. Okay? So that's if you're allowing it to go all the way to infinity. Let's look at another type of problem. Hold on, plug that through. Alright. I've got, I don't know, let's make it a sodium nucleus. I've got a sodium nucleus. Now, this sodium nucleus, there's only one type for what we're studying right now. There's only one type of particle I care about in that sodium nucleus. What is it? Protons. How many protons does sodium have? Good. There are 11 protons in sodium. You get that off the periodic table, right? I don't have to tell you that. By the way, if I put an atom on the test, I will not tell you that. Okay? You got to look at the periodic table. Atomic number 11. Okay? Atomic number 11 up there. So it has 11 protons. I'm going to take a single proton out here. I'm going to take a single proton. Let's try to make this relative size where it might be easier to see what's going on. right? I'm going to take a single proton, and I'm going to shoot it at the sodium nucleus, right? This thing's going to go, it's going to keep coming and coming and coming and coming and coming, and it's going to slow down as it gets there. Does that make sense? I mean, positive and positive repel each other, right? And so this proton, I'm shooting it at the sodium, but as it gets closer, it's being repelled by the sodium nucleus, meaning that it's being slowed down. So what's eventually going to happen to this guy? Good. It's going to slow down, slow down, slow down, stop, and come back the other way. My question to you here is going to be, what distance x, at what distance x does this proton turn around and go back the other way? At what distance x does this proton turn around and go back the other way? Now, let me set you up for this, right? This is not that hard. In fact, it's the exact same thing you just did, just backwards. Just backwards. It's an identical problem, just backwards. Now, I'll give you the velocity. V equals 4.5 times 10 to the 5th meters per second. I'll give you the initial velocity. I'll give you the initial velocity of this proton. Okay, where it starts out at. What's the final velocity of this proton? 0. Okay, so the final velocity, all the way over here, V final, will end up being 0. Yeah, it actually stops, turn around, and goes the same way. The exact same way that if I throw something up in the air, right, there's a force pulling all things down. Right, if I throw something opposite, just pulling it down, my marker goes up in the air, stops, and then turns around and comes back the other way. And it's for that split second, right? That instant, that it takes no time to do, that moment of time, it goes up, stops, turns around. But for a split second, the velocity is 0. Now, here, thinking this through, I'm going to set you up and then let you try it. Change in kinetic energy equals negative Q delta V. Correct? Change in kinetic energy equals negative Q delta V. And I can calculate the change in the kinetic energy. This is going to be 1/2 mv final squared minus 1/2 mv initial squared equals, and I know the charge, negative Q, right? I know the charge of this proton. Yeah. We're going to assume that this proton shot from very far. It is shot from very far away, infinity, which means the initial voltage is going to be what? 0. Shot from very far away, the initial voltage is 0, so this would be Vf minus, and I'm going to go ahead and put in 0 for the initial voltage. Now, looking at this, final velocity is 0, right? So this entire term here is going to end up going away. Yeah? I know the mass of this proton. I know the initial velocity of this proton. I know the charge of the proton, or excuse me, I'm looking for I'm looking for the distance away, right? I know the charge of the proton. That lets me solve for the final voltage. Yeah? So I will know, that doesn't stand for velocity, I will know the final voltage this proton stops at. I will know the final voltage point this proton stops at.
Use the voltage equation for time radius.
Excellent. Then I can use voltage equals KQ over R to solve for R. All right, so I'll give you a little bit to do that. Here, calculate the voltage. We said the final velocity is 0, so this entire thing goes away, leaving me with a negative 1/2 mvi squared, right, equals negative Q final minus initial voltage. Initial being,
So it's just Vf.
initial being 0, just making it the final voltage. Okay? All right, let's plug in some numbers. 1/2 m. What's the mass of this proton? 1.673, is that right? Times 10 to the negative 27. Initial velocity, 4.5, times 10 to the positive fifth, squared, minus, you have a negative equals a negative q, so q here is 1.6 times 10 to the negative 19, times the final voltage. Okay, so yeah, now, working this step by step by step. And I actually want to do this one number at a time here just to make sure we're getting things. Okay? So please give me just what 4.5 times 10 to the fifth squared is. When you're doing that, be careful to put parentheses around the 4.5 times 10 to the fifth and then stick a squared on that. Okay? Be careful to do that. So what's that come out? Do you have it? Okay, question. Good question. That was one of the things that was given to you in the problem. I got to shoot it at it. Now, if I didn't give you that, this problem's impossible. Right, Gladys? Right, okay?
Right.
Yes, just nod your head and say, right. Okay. So what is...
I got 2 points.
All right, hold on, guys. Please pause. I got too many people talking around the room. Okay. Yes, and then yes.
Do you do the velocity squared times the mass and then the 1/2, or do you do the 1/2 and the mass times the velocity?
Doesn't matter. Shouldn't matter at all. Right. 2 times 3 is the same thing as 3 times 2. Okay, so it shouldn't matter. All right, so give me, please, Daniel, the 4.5 times 10 to the fifth squared. Yeah, that sounds good. Is that what everyone else is getting? Yeah? All right. So I'm going to work this one little step at a time, right? So they catch any math errors that are happening. Okay. Now all this stuff is just multiply. So I feel like you can enter all this stuff into your calculator in one fell swoop on the left-hand side. Make sure to use parentheses like crazy, just in case, right? Lots of times in calculators, if I see a 1/2, I'll enter the decimal form. I'll put negative 0.5. That way I don't end up messing up order operation somewhere else. Or I need to put my 1/2 in parentheses just to make sure something doesn't mess up. Okay. So negative 0.5 times your 1.673, 10 to the negative 27, all that in parentheses times also in parentheses 2.02 times 10 to the 11. All that comes out to be Brooke. Could you give me that whenever you get it? I just saw you typing in. So. And if someone else gets it before her, just raise your hand. Morgan White, you got it?
Negative 1.69.
Negative 1.69 times 10 to the negative 16. You okay so far? Yeah? Okay. Next. Ladies. Yeah. We'll handle that here in a second. Divide, right? Divide both sides by negative 1.6 times 10 to the negative 19. Interesting, kind of pure luck, those two numbers came out almost the same here, right? So, by the way, the two negatives, right? They're going to cancel out. Negative divided by negative is positive, right? So, what do I expect this to come out somewhere around? Order of times 10 to the third, positive third, right? Denominator, numerator, right? Whenever you're dividing, you take the numerator and you subtract the denominator, right? So that's negative 16 minus negative 19, so that's negative 16 plus 19. So I expect this to come out somewhere around times 10 to the third, something like that, 1 times 10 to the third. So what does the final voltage come out to be?
1.05.
I think I heard 1.05 times 10 to the third volts. Right?
You don't even like what we lost there. Exponents, so you just divide there.
No, worry about the exponent. Worry about the exponent. Whatever you do, this entire thing divided by that entire thing is my recommendation. Okay. You should come out with 1.05 times 30.
I got 1.5 times 10.
Negative 35th. What's happening whenever you do negative 35th? You forgot the negative 19. You put in positive 19.
Right, even so.
Something's wrong with parentheses. Use an E instead of times. You can stick parentheses around that. Listen, calculators are your friend. Ish. They're also your enemy. They're also your enemy. They work against you. Okay? You know what you should be doing. You're doing everything right. You just can't get the calculator to cooperate. You've got to learn how to make that calculator do what you need to do. Okay? Another trick you have to have all these tricks up your sleeve. You have to know what the answer should come out to be kind of like. Right? Remember back to vectors, I said, look, if you know that it's supposed to be in quadrants 2 or 3, and it gives you something over quadrant 1 or 2 or 1 or 4, it isn't right. At 180 degrees, fix your calculator's issue. Remember that? Same thing here. This rule, and you need to get good with this, or at least be able to do it. This rule of exponents, right here, negative 16 divided by negative 19, whenever something's divided by something smaller than itself, right? Think about 1 divided by 0.1, right? Something is divided by something smaller than itself, the number comes out bigger, right? 10 divided by 1 would be 10, right? 10 divided by 0.5 would be 4. Whenever we start getting less than 1, we're going smaller and smaller and smaller, the number's going to come out bigger, right? Bigger. So this negative 16 divided by times 10 to the negative 19, the rule is you subtract the denominator. Negative 16 minus negative 19, that means you're going to add, right? Negative minus subtract the negative means add the opposite. So I expect it to come out times 10 to the third. That looks great. Now, coming down here to actually find the distance away. So I got 1.05 times 10 to the third equals K 8.99 times 10 to the 9th. Q. Now Q is going to be 11 times the charge of a proton. 1.6 10 to the negative 19. Now, let me come back in here and let me erase just that parentheses, because here's another spot your calculator might try to mess you up depending on what it's doing. It might try to do 11 times 1.6 and then erase all of that to the negative 19, especially if you're using a multiplication symbol instead of the EE button in there. So my recommendation here is use even more parentheses. That's my recommendation. Use even more parentheses. Use parentheses like crazy with your calculator. Okay? All divided by R. Okay? So what that tells me is R should be equal to 8.99 10 to the 9th times 11 1.6 10 to the negative 19 divided by my 1.05 times 10 to the third. This should come out to be very, very small. What does it come out to be? AK.
20 times 10 to the negative 11.
I got 1.5 times 10 to the 9.
1.5.
Yeah, I got 1.5.
Negative 11.
1.5 times 10 to the negative 11 meters is a possible answer. Right? An angstrom is about the diameter of an atom. Okay? Atom diameter, that's with the electrons included. Remember, the electrons are a long ways away from the nucleus. Are, so many angstroms. That's times 10 to the negative 10. Right? That's 10 to the negative 10. All right? Picometers times 10 to the 12. Whenever you start talking about picometers, we're starting like 1 picometer. We're starting to get down to the order of the nucleus itself. Right? That distance right there means that the proton went through the electron cloud, somewhere inside the electron cloud, as it's first approaching the nucleus, it goes almost nose to nose with the nucleus. It gets really, really close before the force finally gets large enough to turn it around and go back the other way. Turn it around and go back the other way. Two types probably work, right? This one, where you have an initial velocity, that means you have an initial amount of kinetic energy. I ask, what distance does it finally turn around at, right? Where do we finally cancel out all that kinetic energy? In this one, we start out with no kinetic energy, but there's voltages, right? And we allow it to move, we see how much kinetic energy we pick up, right? Combination of these two equations. On this problem or the last one. Combination of these two equations, like I'm doing down here, right? You solve for, one way or the other, you solve for the voltage being put out by the big charge, right? V equals KQ divided by R squared, that's a big Q, right? And then use that with the work equals negative little q times change in voltage with potential difference. And we can work backwards, right? Work equals negative q delta V, calculate V, plug that in to V equals KQ over R. See the distances. Two types of problems. Any questions about this? All right.